It all started with this, the simple switch, and we've come a long way since then. In this episode, we'll look at the modern electronic analog switch and how to select and how to use them. In the beginning, there was the mechanical switch, and life was good. A switch, of course, is a way to route electrical signals. In the simplest form, they just make or break a circuit by physically separating some metallic contacts. And on a couple more sets of contacts called poles, and you can control more than one signal at a time. Add on more positions or throws, and you can then route those signals to more than one destination. Which gives us the single pole, single throw switch, which has a single set of contacts which can route the circuit in a single direction. Or how about a double pole, double throw switch, which has two poles, each of which can route in two different directions. Or a whole host of other throws and poles which have been developed over the years. But mankind, being lazy, didn't want to spend all that effort to flip the mechanical switch, so he invented the electromagnetic relay. With just a bit of electrical current, would use a small electromagnet to switch itself, with all the same combination of throws and poles as the mechanical switch. And life was good again. But ultimately, mankind needed something much smaller and less expensive and more reliable. Was there an electronic equivalent to these switches? Which brings us to the heart of this episode, which is the FET, or the field effect transistor. A FET is a solid-state device. There are no moving metal contacts inside it like the mechanical switch or the electromagnetic relay. It's built on a silicon substrate like most semiconductor devices. A series of N or P doped wells, depending on the type, create the drain in the source or the input in the output of the FET. The area below the gate metal is a semiconductor. It can be made a conductor or an insulator, depending on the charge applied. Functionally then, it looks just like an electromechanical relay. Apply the right voltage to the gate and the switch contacts will close. Now, just like all semiconductor devices, it has a maximum voltage it will tolerate across the contacts. This is known as the VDSS, or the breakdown voltage. There are two fundamental types of FETs, the N channel and the P channel. Physically, this has to do with the doping type of the wells in the semiconductor itself. But from an applications point of view, it also refers to the way that you bias, or you apply voltages to the FET to make it work. An N channel FET turns on and allows current to flow from drain to source when the voltage at the gate is higher than the voltage at the source pin. Got that? The P channel FET is the opposite. It turns on when the gate voltage is lower than the source voltage and allows current to flow from the source to the drain. Now, it's generally easier to manufacture N-channel devices, which means that they are less expensive and there's more varieties available. P-channel devices, however, are easier to design with, so there are still a number of them available. So to turn on a FET, the gate voltage must first reach a certain level, known as VGS threshold. Now, this varies from less than a volt to a couple of volts. It occurs on a point of the voltage curve which we call the plateau. And just like a mechanical switch, it can't close its signal path or its contacts in zero time. In a FET, at this plateau, the control voltage must overcome the charge, or the QGD, across the gate and drain before it can allow the signal to pass. This results in a short but a measurable delay to turn on the device. And while in this mode, the device dissipates some current which results in loss. There is no such thing as a perfect conductor. And even in a mechanical switch, there's some resistance. Now, once the gate drain charge is overcome and the FET turns on, there's still a resistance within the device known as the resistance drain to source, RDS on, or often just R on. It's typically on the order of a couple ohms, or as low as a couple milliohms or thousandth of an ohm. But at high current or at small signal strength, Even a small resistance will have an impact on your signal. Now, why all this detail on the FET? I thought this lesson was about analog switches. Well, it is. But the FET is what makes up the heart of the analog switch. So by understanding the fundamentals of the FET, you can understand the specifications for the entire switch. So now let's look at the key parameters in deciding on which of the many analog switches which use FETs that you should be using. These first parameters, ironically, are the same thing that you would specify for a mechanical switch. First, the switch configuration. This is the number of poles and contacts, or the number of unique signals and path that you need to control with your switch. Just like a mechanical switch, you can get an analog switch that's a single pole single throw, single pole double throw, double pole double throw, etc. VSW, or the switch voltage. This is the maximum voltage that you can apply to the inputs of the switch. Just like you wouldn't use a tiny electrical switch to turn on the 120 volt mains in your house, you need to pick the right voltage rating because they are designed for low voltage or high voltage applications. VSW for most analog switches is a fraction of a volt, up to perhaps a dozen volts maximum. You won't be controlling your house with an analog switch, by the way. Bandwidth, or the frequency of the 3 dB point. The higher the frequency signal you try to pass through the analog switch, the more the switch pushes back or reacts due to its inherent capacitance. At some frequency, the signal is reduced or attenuated by -3 dB from its DC level. Now for an audio signal, this means that the signal now sounds only half as loud as it originally was. If you're switching a data signal, the bandwidth determines the maximum data rate that it can support. Other important parameters in selecting an analog switch include the on resistance. This is a function of that FET that lives inside the switch. In general, the lower the R on, the less the signal passing through the switch will be attenuated. In a mechanical switch, R on is pretty much constant. In an analog switch, R on will vary with voltage, temperature, and load current. A measure of this variation is called delta R on. Selecting a low delta R on device will minimize your signal distortion across the entire operating range of the device. The supply voltage, VCC. Remember that a FET has a threshold voltage before it will turn on. So the analog switch has a biasing voltage required to power the switch. Lower VCC also means that there is less headroom between the maximum signal and the supply voltage. Some applications like audio may actually require a negative voltage capability. The on-state capacitance. Again, a characteristic of the FET which physically resembles a big capacitor on the silicon itself. A bigger FET will therefore have a higher capacitance, which will reduce the maximum bandwidth of the switch. The input voltage range. This is the maximum voltage that can be applied to the input of the switch. It's different than the supply voltage VCC, or the voltage of the control pin on the switch. The enable-disable time. Remember the gate drain charge? This is the effect that it has on the analog switch. It's the time that it takes for the switch to change states from the time that the enable pin has been triggered. The select control pin threshold levels. This is the voltage required to switch and close the contacts. It relates to, but it's not quite the same as the gate voltage, because there can be buffers, inverters, or even level shifters between the outside pin and the FET. Since analog switches are usually controlled by digital circuits, these levels are usually set to match the common TTL levels of 0.7 and 1.4 volts, or CMOS level of 30 and 70% of supply voltage. And the package size. Finally, how small do you need the device? Because this is where an analog switch just really flat out beats the mechanical switches. Analog switches come in packages as small as 1 millimeter by 1 millimeter. Imagine trying to push a switch that small with your finger. Now there are several different categories of analog switches, but the easiest way is to think of them in 3 different groups. Number 1, general purpose switches. Data switches and bus switches are all involved in switching and routing digital data signals. You'll find them in network routing equipment, USB hubs, etc. While they are indeed analog switches, they spend most of their time routing digital signals. Video switches and audio switches are functionally the same, But the FETs have been tuned for a very specific application, for low attenuation or low signal loss for audio, and high frequency response if you want to route video through them. And finally, load switches. Load switches are analog switches with very, very low frequency response. In fact, they operate at DC. They are so specialized that we'll actually dedicate an entire episode on just how load switches operate. Now, this is one of the most common general purpose switches, the 1G66. The -66 suffix is an industry standard number for a single pole, single throw analog switch. It works across all the most common digital voltage levels from 1.65 to 5.5 volts. It's low power and it comes in a variety of small packages. You will find this in such applications as routing memory signals out to an SD memory card, or connecting a number of analog inputs to a single A to D converter on a microprocessor. This is an application for its friend, the 74LVC 1G3157, which is the single pole double throw version. It's common for electronic devices to require testing at the assembly site to make sure that they operate correctly. For this, the tester needs access to some of the internal connections of the device. But that also requires another extra expensive connector. So why not just use the connector that's already there, like the headphone jack, for testing purposes? Now, once the test is done, the test pins are no longer required, and in fact, they become a liability. The micro could be damaged by a stray signal, or somebody could actually get into it and reprogram the device. In this example then, the 3157's job is to make those pins available for testing, but then to disconnect and hide them once the product is in the consumer's hand. It's sort of a magic trick for those pins. Now you see them, now you don't. Here's a common application for an audio analog switch. In fact, you may have one in your pocket right now. There's a physical connector on the side of your mobile phone for a wired headset. However, if you have a Bluetooth headset, you may want to route the audio signal from that connector to the Bluetooth transceiver instead. The perfect application for an analog switch, like the 4684, which is a double pole, double throw switch, because good set headphones are stereo, of course. No mechanical contacts, no worry of dirt, reduced popping during the connection. Another important feature of an audio analog switch is frequency linearity. You want the R on, or the attenuation, to be the same for any audio frequency passing through the switch. This way, the signal isn't corrupted. The relative levels of bass and treble stay the same as they pass through the switch. Video switches have been tuned for specific high frequency application that video signals need, up to several hundred megahertz. Now this switch, the NX5 DV715, does way more than just that. It's a complete VGA switch. It switches the RGB signals, buffers, and the monitor ID lines. It translates the control signals, and it even provides ESD protection on the VGA connector, all in one package. You'll find a switch like this on the docking station on your laptop, for example. You dock the PC, and the VGA signals are routed up to that big monitor on your desk instead of the internal LCD display. Video switching can also be found anywhere that there are video signals, like security systems, KVM ports, AV equipment, rear view cameras in cars. There's all sorts of applications for them. A bus switch is made to route high-speed memory, data, or control buses inside equipment. Since a bus means multiple wires going in the same direction, these switches tend to have many poles. This one, for example, is a 4-pole double throw. You might find a device like this, the 3257, used to allow a workstation to access different banks of memory, or a network controller to switch the paths in a high-speed Ethernet signal. These switches are built for speed. In fact, the delay through a CBT or a crossbar technology family is typically less than 1 nanosecond. By comparison, a data switch is usually used to describe a switch tuned for a very particular type of data, like USB or HDMI or MHL, which are all connector standards. The NX3 DV221 is such an example. It's made for routing USB signals. With one of these, you could have one controller on your motherboard connected to 2 different USB sockets. Let's face it, you don't use all those USB connectors at the same time anyway, so why dedicate a USB controller to one? Share the expense by sharing the connectors. Finally, load switches. Again, we'll cover this more in another episode, but like the name indicates, a load switch is used to shed loads. You don't use all the features on your mobile phone at the same time. How often do you really need Wi-Fi and baseband radio and Bluetooth transmitters and the backlight and the touch screen and the power all going on at the same time? Well, if you're a power user, maybe you do. But the average power simply doesn't need all those subsystems running at the same time, consuming battery life. By putting a load switch on each of these subsystems, the phone can turn on just the devices it needs for a particular function and leave the others switched off. Besides turning loads off and on, load switches can also integrate over voltage protection, under voltage lockout, over current, over temperature, etc. Like I said, there are so many features in modern load switches that we will spend an entire episode just talking about those. So, we've seen a lot of new information today. Let's summarize. Remember that the heart of every analog switch is the FET. Understand the basics of the FET, and the rest becomes pretty easy to figure out. For a general purpose analog switch, the FET is tuned for best cost, which means it's the smallest size. It has a reasonable R-on, a reasonable frequency response, and thus is great for reasonable applications. An audio switch has a FET tuned for the lowest possible R-on so that the signal gets in with little attenuation. In addition, that FET is tuned to have a linear frequency response so that all the various frequencies of sound pass through at exactly the same voltage level. The analog video switch is tuned for video frequencies, runs at hundreds of megahertz. The trade-off is that the R-on might be higher, but since there's usually a video amp somewhere else in the chain, that can be made up. Bus switches are made for flat-out performance. Bus signals are digital, so linear is not so much an issue. Data switches are built and tuned for a particular type of data. Switching USB signals, get a USB switch. Switching MHL, get the switch tuned specifically for that application. And finally, load switches. These guys are the pack mules of the analog switches. They have gigantic FETs so that they have the minimal R-on and can pass very large currents for their size. Frequency response and linearity, hey, who cares? They just run at DC. And there you have it, the family of analog switches. What they do, how they do it, and most importantly, how you can use them to make your next design the most efficient.